I used to work mostly on natural language processing and language understanding, but I moved about a year ago to a team focusing on robotics and reinforcement learning. So in the last year, I've been trying to make the switch and learn a lot more about RL and robotics. And I'm based in Berkeley area, and I studied at Stanford and University of Toronto before working.
Nice.
Do I pick someone?
Yeah, feel free. Or we can just go ahead.
I'll pick Hay. A-T-Y? I'm not sure the name.
Yeah, he's our mysterious guy because we couldn't see your name in your avatar.
Not sure if your mic is working, but I can't hear you. If not, maybe we go to the next person, Leela. Hey, if you come back, give us a hey.
I'm sorry, I kind of forgot his name as well. But he's I remember he works as a software engineer. Maybe we'll get back to him. But what about Krishna? Would you like to do a reintroduction of yourself? I don't know.
Sure. So I'm Krishna. I'm currently working as an AI software engineer at Johnson Controls. I've been working in reinforcement learning for about 1 to 2 years. I implemented some of the algorithms. I got a break in between focusing on other stuff, but I wanted to get back to reinforcement learning and pick it up from there.
Great. Niju, are you here? Rosalind, would you like to give an introduction of yourself?
Oh yes, no problem. So, as you already said, the name is Roslan Dosa. Currently full-time PhD student in Japan, working in reinforcement learning, namely long horizon tasks solving.
Niju, I saw you popped up here. Would you like to give an introduction of yourself?
Hello guys. Myself Niju, and I'm working as a software engineer. I'm working in industrial automation. It's a totally different domain. So for the past 1 or 2 years, I'm just learning about RL and deep learning on and off. So it's a totally new domain for me. I'm just trying to learn as much as everyone. So that's all I'm trying to.
Yeah, that's great. And I think the last person. Hey, is your mic working?
It's me.
Yeah,
right, guys.
Yeah.
So.
Would you?
Yeah. So my name is Lucas, and I'm a software engineer. I've been doing it for a very long time. I'm mainly building like distributed systems, and I've been into like RL for a few years. I'm doing it, for by myself mostly. I think that RL is the most powerful algorithms currently we have right now, and I'm mostly interested in games, using it for games, and happy to be here and be part of this learning group.
Well, thank you for joining us, and I want to say sorry, Lucas. I kind of forgot your name, but it's sometimes it's kind of hard to remember.
No, it's okay. No worries.
Yeah, is there any reason that your Google account name is just HEY?
Oh, yes. If you want to, it's actually the name because I'm the to. It's the name of the piano, basically. It's
Oh,
because
okay.
I'm the as well. I'm a musician as well. You know,
Oh,
so,
okay. Oh.
yeah. So yeah.
Okay, makes sense. All right, I think everyone has introduced themselves. A big welcome to for Krishna. A big welcome for everyone who have been coming to the reading group. Thank you so much for keeping it up. And let's begin. So, how many of you read had a chance to read the paper on ACER?
So far, I did the first pass, but honestly, it's quite a cryptic paper. I
Yeah,
would say.
yeah, no doubt.
Yes. Fortunately, algorithm is much easier to understand.
Yeah, it's like if you read DDPG paper, the way to update it's so easy, and this ACER paper just keeps blabbing out math and.
But I guess upping of value comes easy, so.
Yeah. Well, keep that thought. We'll get into it. But yeah, so okay, so I think maybe it'll help if I just kind of give a presentation on some of the intuition behind the paper. So I did this presentation trying to mainly give you just the ideas, and I unfortunately didn't go through every piece of information in the paper. I didn't cover the continuous domain and the trust region optimization because I think they're a little less intuitive in terms of what they're trying to do, and it's also very math heavy, kind of very difficult to read. But let's begin. So today we're giving a presentation on the ACER algorithm, also known as, in this paper, sample efficient actor critic with experience replay. And the link to this presentation is already linked in the Slack channel in case you want to check it out at the same time or have a copy to yourself. So first of all, the paper is in this archive site. Is an archive, and also I included the annotated PDF, annotated by myself. Sometimes I find them to be helpful to understand what the paper is trying to say, especially when I try to highlight a lot of things that I think is important. And I included a description of what those color means. So, for example, purple means important tricks and details. Yellow means general emphasis. Orange means important assumption. Pink means intuitive plausible inference, which may not be true. And blue are questions. So feel free to check those out. I'm actually going to open it maybe on this half of the screen. Okay, let's continue. So what's the problem? The problem is that the policy gradient methods require sample to be collected on policy and therefore could be very sample inefficient. So a typical policy gradient method would be something like advantage actor critic. And if you look at a paper for advantage actor critic, they always require you to collect the samples and then you optimize over the samples you collected. And you need to do that for every time you're trying to do a gradient update for the actor critic, for the advantage actor critic. And that could be very sample inefficient. When you have limited samples, you might want to find out different ways to optimize so that you can learn with a limited number of samples. So here we present a quick rundown of the paper. In general, policy gradient generally looks like this, where you have the log probability of executing a particular action given the current state, multiplied by the advantage estimator. And over here, usually, when you see the policy gradient, you just see Let me try to find a shape. Usually in a policy gradient method, you just see this, whatever is on the right? You see the advantage times the log probability. However, here has a summation over all the time steps. So that's just saying not only you're optimizing for a particular time step, but rather you're optimizing over the entire trajectory for each of the time step in the trajectory.
I think both definitions are actually equivalent, because when there is no sum over t bigger or equal to 0, they usually put g subscript t. So just the gradient at that time step.
Yes, and when you're doing the implementation, you're really doing this, because if you look at the implementation, it's always advantage times the log probability. However, the advantage at a particular time step, the advantage array is essentially a collection of the advantages over all of the time steps in the trajectory. So you're always doing this.
So you mean like the expected future advantage, not just the advantage at this time step?
Perhaps not. Yeah. So let me maybe illustrate this with code. Maybe that'll be clearer in terms of expressing what I want to say. So this is generally the A2C algorithm, right? And you just kind of run it, and then if I control C out of it, and then if you take a look at how you would optimize the policy loss, you multiply the advantage times the negative log probability, right? So the advantage is up to a certain step, and the negative log probability towards a current step. So if you take a look at this, each of those elements stands for a time step t. This is t equal to 0, t equal to 1, t equal to 2, 3, 4, 5, 6, right? So I think that's what the objective is trying to say over here. You're optimizing over each of the time step in your collected sample. In this case, it's t equal to 0, 1, 2, 3, up until it finishes. Does that make sense? Is that what you were trying to say, or not really?
I don't really understand why there is a need to add the sum over t again.
I don't think there is the absolute need for it. Like even
there's already the expectancy over the state and action distribution. So because actually it may be a little bit early, but in this paper they use future lambda returns, right?
Yes.
To compute the Q value, for example. So I'm wondering if they are already introducing that concept of future returns into the gradient itself.
What would future return mean? I guess.
For example, instead of a TD lambda, the default TD just takes one step, the reward of one time step, to compute the difference, the TD difference. But the return-based method will take, for example, 5 steps ahead.
Right. So by all means, this AT right here could be something like GT. So the return from the current time step T to beyond. Right.
Okay.
So
we should probably go ahead, and maybe it will be clearer later.
Yeah, maybe. Let me try to say something before we jump on, and then we'll go on. If you see the return that is used to calculate the advantage, it's really this array over here. And this 26 essentially could be, this, if you don't use the value function to reduce the variance, then this could be the GT over here. and you're summing up of all such instance of this return. So you're doing this for this, then this.
Okay. Would you say the summation over time steps applies only to the advantage function, or both advantage function and the log probability?
I think this summation is merely trying to tell you that, when you do in the calculation, you're not doing this. You're not doing the negative log probability of a particular time step times the advantage of a particular time step, right? It's trying to say that you're really doing it for a collection of them.
Okay, and then some of it. Next, I got it.
Yeah, I think that's what it's trying to say. That's why you see the summation. I was a little confused too, but I think this makes sense, I guess. Okay, let's continue. Right. So this is a general policy gradient that that would look like, and the problem is you need to collect the samples based on the current policy pi theta, and that could be problematic. What if we want to optimize using off-policy data? Suppose we retrieve a trajectory, state, action, reward, a behavior policy, probability distribution, and then the next state until so you have this k-step trajectory. What if you want to optimize your policy using the off-policy data? So the author suggests that the off-policy gradient, off-policy gradient could be calculated using this, where rho is the ratio between the probability under the target policy and then over the behavior policy. And target policy is a policy that you want to optimize, and then behavior policy is something that is used to generate the data. And if you want to, I kind of forgot to include the slides here, but if you want to get some intuition as to why is there important sampling, it has something to do with returns. Again, I'm sorry I forgot to include related slides. I thought about it, but I kind of was too focused on the paper. But if you search for important sampling in Richard Sutton's book, and I think at some point they gave a really good explanation for why that is the case. Yeah, it had this important sampling ratio. It has something to do with when you take the expectation, basically the quotient kind of cancels out, and then you're left with the correct policy gradient. I'm sorry that is vague. I'll try to find the correct pages and maybe send it to the Slack channel once this presentation finished. But for the moment, just imagine this important sampling ratio as something that will give you the correct policy gradient. Right. So the problem is that the product of this important sampling ratio could blow up, because this could be anything. What if you have something like 1.2 over 1, and then you have a lot of them, and 1.2 times 1.2 times 1.2, essentially you have no control over it, and it could blow up. And that would be very bad for gradient-based learning, because your logics will blow up, everything will blow up, and you'll end up with a useless policy. So Degris et al., I think he works with Richard Sutton and says no problem. So forget about the product. You can just use a single instance of the important sampling. So instead of the product over here, you can just use a single one of them to approximate the off-policy policy gradient. So this is equation 4. 2 important facts about this equation must be highlighted. So first one, notice that it depends on the Q function of the behavior of the target policy pi, and not the Q function of the behavior policy. So therefore, we need to estimate the the Q function of the target policy because we don't know it. And second, that is the point that I was trying to make. We no longer have a product of importance weights, which is this part of the equation right here. Instead, we only need to estimate the marginal importance sampling weight, which is just this single one PT. And how do we estimate this, the Q function of the target policy? That's where the paper talks about they use this thing called a retrace algorithm. And an important thing to notice is that even though it is a experience replay, usually in experience replay, we sample a transition, right? If we take a look at our Q-learning kind of algorithm, I wonder, can I make this a little larger? Yes. If you look at our Q-learning source code, you'll find that when we sample from the experience replay, we have the state action reward, next state, and then a terminal mask. However, when you are using ACER, that is not the case. Instead, you sample a trajectory. So that is a huge difference. The experience replay used in standard method like DQN, they sample a particular transition. However, when you're using ACER, you sample an entire trajectory. Well, you sample a piece of the trajectory, I guess. The trajectory could be k of k length when the could be of length 5 when the episode is of 100 length long. So important things is that they have to be sort of sequential. And that's how you can sort of calculate the retrace of the Q function of the of the target policy pi. And the way you calculate it is this is also the part the author doesn't really give like a intuition as to why that would work. But it has something to do with importance sampling, adjusting the correct, basically adjusting for the correct Q function. And over here, they truncate the importance sampling. So that helps with the importance sampling being, blown up. But this is how you calculate the retrace. And then you start with, eventually when this reaches the end of the sampled trajectory or sampled sequential data, this becomes 0 if the state terminate at that particular state. Otherwise, it's the value function of that state. From an implementation standpoint, I get the chance, because it's kind of related to my research, this week I actually got some chance to play with it. And I can kind of show you what the Q-trace, the initial calculation will look like. Essentially, you will, the first retrace, which is at the end of the sequential data, is calculated by the values times the mask. So if you think about it, it's saying if at a sequential data that is sampled has ended at the last time step, then the value should be 0 because there are no future states. Otherwise, it should be the value. So that's kind of how the retrace is calculated. And then notice, the importance sampling row is truncated. And then it's equal to the minimum of clip ratio and the row itself. So if you think about it, what that means is that it has an upper bound. The upper bound is C. The row could be, imagine if C equal to 1, then if row equal to 1.2, the minimum of 1 and 1.2 would mean this row bar equal to 1. So it has the upper bound, essentially. It's also interesting why they don't bound from below. Perhaps because when you bound from below, it doesn't cause as much of a problem as if you don't bound from above. Because if you don't bound from above, then the importance sampling could blow up numerically. Right. And then by using this formula, you could get a retrace Q function, which will serve as an estimate for the Q function of the target policy. And then you essentially optimize by using the retrace Q function as a target. You minimize the mean squared error between them. That's essentially how you optimize over the critics.
I have a small query.
Yeah.
When we mention a Q value at a given state and an action, so it indicates the value of a state if you take an action and if you follow a given policy from the future time step onwards.
Yes.
What does Q retrace indicate here?
What would the Q indicate here?
Q retrace.
The Q retrace is an estimate of the Q function of the target policy because we don't know what this Q pi is, right? Because as you said, a Q function is assuming you executing given a state and you executing a particular action and following that policy onwards. But here we don't know about the Q function, so the retrace. Again, this paper doesn't offer much of an intuition on why the retrace is a good approximation for QPy, but it's sort of like an approximation assuming. So this you can imagine this Q retrace is sort of estimating what would happen if you had followed the policy pi. Does that make sense?
So does it function like a critic?
Yes, it's a critic because here we have an actor critic algorithm. Critic is usually serve as the a baseline to reduce the critic is usually used to reduce the variance of the policy gradient.
Okay. And I guess at least one thing. So at least the paper mentioned that they tried various mechanisms and they kind of concluded that the retrace algorithm was best.
Yes, indeed. I think in the paper they mentioned quite a few possible techniques as related works. Somewhere over here.
Section 3.1.
Yes, indeed. But they didn't mention any other technique in section 3.1, did they?
They mentioned the tree backup method of Prekup et al. It's in the first line of 3.1.
Oh, I see. Yes. They also experimented with other techniques, but retrace is what the paper is focusing. Yeah. Thanks for the catch. So that's how they estimate a critic, and now here comes the really, I guess what you could call the meaty part of the paper. Here is how you would improve the policy, how you calculate the policy gradient. So first of all, you have the left-hand side, which is the results from the Degris et al. Is essentially the off-policy gradient. One of the main contribution of this paper is that they claim to add this term on the right that serve as a bias correction. And I want to say this is probably the worst part about the paper from my perspective. One of the worst part, because it doesn't offer any explanation. Like it says, the correction term, the second term in equation 7, which is this term, ensures that our estimate is unbiased. And that's it. There's no appendix, no proof. It's kind of frustrating to read on this part. Like if I search for bias in a paper, oh, maybe I was wrong. Retrace can be interpreted and bias correction. But it talks about retrace. It doesn't talk about the policy gradient. Yeah, probably I'll have to look into it. Maybe they do claim somewhere that it's some sort of proof. That somehow it is unbiased. But yeah, from the phrasing itself, I don't see why that would be the case. I remember when I was learning statistics, there's a very specific way of you proving something is unbiased. Like a famous one would be proving sample variance is unbiased. And you have to go through this process of essentially saying the expectation of the sample variance is equal to the variance of the population. So I don't know how. I've never seen a proof on anything related to bias with respect to policy gradient methods. So that's something that was very frustrating for me to read. It's like a claim right there. But perhaps they included a more thorough analysis in the appendix somewhere over here. But anyway, so let's at least try to take a look at what it's trying to say over here. So the off-policy gradient part on the left-hand side of the equation makes sense. On the other hand, the right-hand side of the equation is a little bit, I guess you could say, confusing. But what it's trying to say is instead of using the AT, you're getting the expectation of an action from the policy. So when you do the actual calculation, you need to calculate this quantity on the right hand side for each possible action, and you sum them up. That's just how you evaluate an expectation. So it's saying for each action, you should sort of multiply by the probability of that action times the important sampling of that particular action minus this bias correction term divided by that, and then times the log probability and the Q retrace or Q pi. Yeah, I don't know. How do you guys feel about this part of the paper?
No feelings.
No feelings. Okay. Right. A couple things to notice is that so the author suggests that this equation has some interesting algorithmic effects. So, namely, the part over here is truncated from above. So this is at most 1. And then also on the right-hand side, it's also at most 1. Because no matter how large this will blow up, the quotient between them will eventually converge to 1. Sorry. Yeah, but it's really hard to read this part because it doesn't offer a lot of intuition as to why that is the case. But that's essentially the policy, the off policy gradient for this paper. You just kind of replace the Q pi with Q retrace when you actually calculate a gradient. You use the retrace as an approximation. So that's about, for me, that's basically the paper, the some of the more important results. And then the author went on to talk about how they do the efficient trust region optimization to sort of make sure the policy is the updated policy is in a sense within a certain distance from the original from the pre-optimized policy. And they have this sort of a sentence suggests the average policy will be updated sort of softly, much like how we update the Q network by using our target network using this kind of soft update. But yeah, the paper talks about it in depth and it's very mathy over here. It's kind of hard to read. It's even harder to read when you try to read the pseudocode. The way how they calculate things with respect to the trust region updating is very long, I suppose. But anyway, they were able to achieve very good sample efficiency. And the graph over here, it's a little bit confusing because some of these lines, they went up all the way to the top. So anyway, so on the y-axis is the normalized reward calculated by human normalized score. So I would imagine a 1.0 here would be sort of the average reward that a human would get. And it's showing that within, given the same number of training time steps, ACER with 8 replay is able to achieve great sample efficiency. But I don't know why they just stop it at 1.5, because the blue lines doesn't stop at 1.5, and I don't know why they didn't, fully finish the algorithm until 900 million steps. So there's a little inconsistency, I guess. Maybe they're running for the same number of hours. That's why you see, they're being cut off at different rate, I suppose.
In the legend, I see like for the plots that are stopped quite early, they use a bigger replay. I'm not really sure what that means, but it's probably the reason for it to stop so early.
I think the A replay means thread, right? Because it's sort of based on A3C, so it's using multiple thread to do this, maybe? Like, what does A replay even mean?
Exactly.
Let me search for it real quick. To compare different agents, we adopt our metrics, the median of human normalized score over all 57 games. The normalization is calculated such that for each game, human scores and random scores are evaluated to 1 and 0 respectively. The normalized score for a given game at time t is computed as the average normalized score over past 1 million consecutive frames encountered until time t. For each agent, we plot its cumulative maximum. Okay, so that's also interesting. It's a maximum, not the average. Cumulative maximum median score over time. Jeez, that's quite a mouthful.
I think the replay part is the next paragraph.
The 4 colors. Oh, I see. Replay ratio. Do you know what that means?
Nope. But I guess they attempt to explain it. The next in the following line, yes.
That's it. Really? Yeah, I don't know what the replay ratio is. Oh, sorry. Yeah, or a 4 replay ratio with a ratio of 4, meaning that we use the off-policy component of the ACER 4 times after using on-policy component. I see. Okay. So you're doing some on-policy updates, and then you're doing off-policy updates. I see. Okay. I see. Okay. Yeah.
So that's probably why, for the same time, it makes less progress. If you can bring back the figure 1.
Yeah.
For the same time, it takes it. It does less steps in the environment, but the performance is also appealing. So.
Mm-hmm. Right.
Quite not too bad of a trade-off, I would say.
Mm-hmm. And something that I say would be kind of surprising is that it would appear that A3C actually performed better than DQN. Oh, I see. Given the same number of hours. Right. That may be true. Okay. Yeah, given the same million time steps, DQN should be... Yeah, DQN should have great sample efficiency, which is shown here, right? It just with...
Are we talking about the standard DQN?
Oh, sorry. Yeah, the standard DQN is over here. The black is the prioritized replay, which performs very well. Yeah, I see. Yeah, that makes intuitive sense. All right. And then the author also shows the results on continuous domains and did an ablation study on the major components of this algorithm. So if we don't do the trust region, then it performs a lot worse. And then they invented this called stochastic dual networks, which I don't know if I want to implement that part. It seems a little bit too complicated. But it performs very well. Well, for some domains, for humanoid, it performs very well, but for other two, it's, I would say, a little inconclusive. And they also did this, no retrace nor off-policy correction, then such a huge difference. And then there's also the no truncation and bias correction. So I would say this result is also a little inconclusive. And in fact, I think even if you don't do the bias correction, at least based on my experiments, it's able to perform just fine. So that would be something interesting to look at. So next week is going to be the implementation week. So feel free to dive into the code and try to implement it. So I'm actually not, depending on what a lot of you guys would be interested in. I don't feel particularly interested in implementing for the continuous domain, because for continuous domain we already have very good algorithms, like TD3 or PPO with tricks, with co-level optimizations. But I would say when we do the implementation, some very useful resources to look into is from Minimal RL. He has the ACER implementation. I would say be a little careful about it. Oh, by the way, so over here, you see the train model on policy equal to true and train policy, train the model without the on policy. I think that's where the experience replay ratio comes in. Right. So a replay. So I think what is being implemented here would have a replay ratio of 1, and then if you train a model multiple times, it would have a higher replay ratio. Something that I would say is that, okay, so this kind of makes me I don't know. It irritates me a little bit. But do you guys see it over here? What this is?
The random constant?
No.
Oh, reward normalizer.
Yeah, this is reward engineering, people. And I try to make the rewards, to be just reward instead of divided by 100, and all of a sudden the algorithm doesn't work anymore. And when you normalize the reward by 100, it performs very well. So I don't know. I don't know about these kind of things.
What kind of environments?
This is Cartpool. So
Cartpool.
yeah, it's also not something that is difficult. And so this is something interesting, right? I implemented a lot of the code based on his code, and what I found is if I don't do the bias correction, and over here I don't do the reward normalization, the reward thing, divided by 100, then apparently it's still working. Yeah, so usually the loss is the off policy loss plus the critical loss plus the loss 2, which is a bias correction. And over here I just commented out the bias correction, and it performs seems to be performing just fine. Converge at about 20,000 steps. And if I sort of add the bias correction back, and it's just so bad. I feel like I probably implemented the bias correction incorrectly. Yeah, whatever. But yeah, this is something I think will be interesting to implement. And from somewhere, I remember reading that Impala, the new sort of policy gradient methods developed by DeepMind that is very distributed. I think they also use the sort of truncated weights kind of stuff, which they call Retrace. But I don't think they do the bias correction, right? If you look at Impala paper, bias. Okay. Yeah, so I don't think they do the bias correction, but yeah, that may be something to investigate. Anyway, so that's kind of it for the paper. And I would say for those of you who would like to try out, implementing ACER, perhaps I should write a better guideline for this, but usually how I kind of start this is by starting from some file. So for example, A2C. What I would do is I copy the file into a new file and just kind of start deleting things. Like, for example, I know ACER used Q function instead of value function because value function only gives you a single scalar value, but Q function gives you, in a discrete domain, Q function essentially gives you the Q value of each possible action. So I know I need to have a different Q function, so I kind of delete that and write my own Q function, and I add related arguments up here. And then for the most part, you just modify the lines that has algorithm logic, and then that's about it. Kind of how you would write code with this. But yeah, that's about what I have for this presentation. Any questions?
So yeah, I have a question, regarding this retrace, because I think this is the main component of this algorithm. So how this relates to TD lambda? Can we think of it?
I'm not certain. I don't know. So let's take a look. Where do they mention the lambda return, or the TD lambda, I guess?
It's probably retraced lambda in the background section, if there is any.
So I want to take a look at. So I would say if you want to dig into that, a great place to do is to look at the literature regarding the retrace, right? It's this 2006 work. I think I might have lost it. Let me try again. Are you talking about lambda returns because you see the Dagger set all use lambda returns over here?
Yeah, generally yes. Yeah, that we use like a part of the trajectories, basically, right?
Right. Yeah, you use part of the trajectory. And if you want to look at retrace, yeah, I would say take a look at this. Take a look at, whoever invented retrace in the first place. Right? I think they'll offer a much better explanation and intuition on what it is. Okay. Yeah. Any other comments or questions?
So yeah, generally, I think it's very interesting idea to of policy gradient.
Mm-hmm.
Yeah, it's a very interesting idea, but terrible paper.
Yeah, it can be very hard to read, and there's definitely some part that when I read it, I was like, I don't know what's the intuition. I mean, the technical part, you can read it. It just it's lacking a lot of the intuition.
Yeah.
But yeah. All right. Does anyone? Like I mentioned, the next week is going to be implementation week. I strongly encourage you to, get your hands dirty and do some implementation. Try to look at the paper and see what you could come up with, and try to look at other people's implementation. It'll help you to understand what the algorithm is actually doing, and some of if you use one of the files that we already have as a basis for your implementation, it's going to help a lot because when we discuss implementation, you can show me your file and I'll be able to follow your lines, and we can sort of it's easier to examine each other's code if we know there's a common structure within it, and also the files that we sort of build all of our algorithms on has a lot of utilities such as seeding, adding time limit, adding a video wrapper if you want to record the agent's performance. So overall, it's supposed to power you and makes you debugging easier and makes it easier for us to discuss implementation. All right. With that said, does anyone have any last questions or comments?
Great job.
Yeah, we will try to go to the paper and get our hands dirty again. Yeah.
Thanks, Ali. Have a good weekend. Yeah, thank you, and you. All right.
Yeah, thank you.
Yeah, thank you, Lucas. Thank you guys for joining. Have a good weekend, and yeah, have a good weekend, guys.
Yeah, you don't have a nice weekend. Yeah, thank you guys. Yeah, thanks.
Yeah,
Bye.
bye.
Nice weekend. Bye.
You too. Bye.
Bye.
Bye, Krishna. All right, Rosalind, it's just you and
Yep.